Hello there. When I've got the webcam plugged in, I have to use a budget headset for a microphone with the 3.5 millimeter audio jack because I've only got one USB port. So the audio won't be as good here as it was for the other lecture videos. Not saying that those were great, but if you hear the audio cut out intermittently, that's the issue. Let's plow through some homework problems now, some of which are very easy and should insult your intelligence. Others, not so much. Let's start with the former. Number 2, I'll pull up the e-text here. Well, the publishers put one dot next to the problem, which is supposed to indicate that it's an easy one. Now, sometimes they rework the order of these problems when they release a new edition of the text so they can charge you more money. And I think they forget to reassign the dots. So occasionally you'll be doing a really difficult problem with 2 dots or 1 dot. You think, what am I, an idiot? This is a really hard problem. And they say it should be easy. So don't take those dots too seriously. Wave on a speed problem. Okay, so we're given the speed of the wave and the tension. And then they're telling us if we'd like the wave to travel faster at 180 meters per second rather than 150, what does the tension need to do? So you think back to the derivation of the wave equation for strings and the formula that we used. Clearly, because that tension's in the numerator, if you make the tension greater, the speed of the wave will go up. So let's look at what to do with the formula here. This formula for wave speed is only applicable for transverse waves on a string. However, there's one other wave speed formula presented in the chapter for sound waves, and the formula is very similar. Okay, so at the beginning, I'll be a little overly pedantic here and follow some guidelines for how to set up a problem. We're given the, I'll call it speed 1 and tension 1. And we're supposed to find, no, we're actually given more than that, aren't we? We're also told what the second speed is going to be. See, this is why I don't like doing this. Okay, we're given the 2 speeds, V1, V2, and T1, and we're supposed to find, that's supposed to be a bracket there, the second tension, which will produce the second speed. So one way to go about this is to recognize that since we're given the speed in the first scenario and the tension in the first scenario, we can use that to solve for the mass density, because the mass density is not going to change if it's the same string. Once you know mu, then you could flip the formula inside out and solve for t. And that way, when you plug in the known value of the speed v2 and the mass density, you could solve for the new tension T2. But in problems like this, it's more efficient to do it the following way. First, write down any constant terms. And I don't usually write the word constant when I'm doing this, but I'm just demonstrating the method here. We know that the linear mass density doesn't change. And the terms which do change are the speed and the tension. So here is the technique. Rearrange this formula so that everything that doesn't change is on one side of the equation and everything that does change is on the other side of the equation. So first, let me square both sides to get rid of that pesky square root symbol. The square of the speed is equal to the ratio of tension to mass density. Mass density is the only thing that doesn't change. So I'll put that on the other side and I'll put the v squareds over here. Mu equals T over v squared. So if you plug in the tension in scenario 1 and the speed in scenario 1, you get a particular number equal to the mass density of the string. If you plug in the tension in scenario 2 and the speed in scenario 2, even though these two numbers have both changed, this ratio has not, because it still must equal the unchanged mass density. And that means we can do this. T1 over V1 squared equals T2 over V2 squared. These two quantities must be equal because they both are equal to the mass density. That's the advantage of doing it this way, because notice we can now solve this equation for the required tension T2. And we detoured around the step of calculating mass density. So if you're interested in the mass density, you would go up and solve for it. But if you don't actually need it, just circumvent that step with this efficient little step. So T2 would simply be, I'll take the ratio of the speeds, enclose those in parentheses, square that, multiply by T1. And there it is. So we just take the ratio of the speeds. And what was it? Originally, it was 150, and we need it to be 180. So 180 compared to 150, square that number, and we multiply by the original tension, and we were told that that was 75 newtons. Maybe you've got the book in front of you so you can see the numbers as I go along here. And I'm going to have to grab my calculator. Okay, 180 divided by 150. I hit equals first, so I know what that quantity in parentheses is. Then I square that and multiply by 75 newtons. And I get 108. I think your solutions manual rounded to 110. Now, could we have gone directly to this formula with, or I should say this formula, without formally writing down this step where you set the unchanged quantity equal to the combination of changed quantities? Well, when I solved for this, I could recognize here, this means T is equal to mu V squared. In other words, tension is proportional to the square of the speed. We can see that right here. The power of speed here is positive 2. You know, if it had been in the denominator, we would have some negative power. But it's very clear that tension is proportional to the square of the speed. And as you get more experience using formulas like this, you might be able to jump straight from this statement to this statement. Since it's proportional to the square of the speed, then if you know the required tension in scenario 1, what you can do is take that tension, divide out the previous speed squared, and then correct for that by multiplying by the new speed squared. The fact that tension is proportional to the square of the speed, that's the reason why T2 is proportional, or is V2 squared with some other constants out front. It's difficult to explain that exactly with the rules there, but obviously this method will always work. But that will make you a quicker problem solver. Okay, here's the best part. Moving on. Numero 7. Okay, can we all just agree that these snapshot versus history problems, history graph problems, are the most annoying ones in the chapter? And strangely enough, I think they're one of the more challenging things conceptually in this chapter. And I don't mind telling you right now that I am not likely to test you on these. However, they're worth doing because they enhance your ability to imagine these traveling waves. So let's go through this, and let me point out the solutions manual for number 5. I think they screwed it up. It's wrong. So hopefully that didn't cause too much frustration. We're looking first at a history graph. Remember, the history graph shows you, if you just focus on one particle in the string and you look at what it's doing in time, how it's going up and down in time, that's what this graph tells you. It is not a profile necessarily of the actual wave in space. So if you were to stand to the side of the string and freeze time and look at the shape of the string, that's not what this graph tells you. Now, there is a relationship between the two, which we'll get to in a moment. But what this graph tells you is how the displacement of a particular particle in the string depends on time. So evidently for this particle located at the origin, so x equals 0 is where the particle is. That's the one we're talking about. At t equals 0, the particle is disturbed and it goes high. It's displaced by 1 centimeter upwards. It chills up there for 2 seconds, and then it falls back down towards equilibrium. It passes through equilibrium, and it has its maximum displacement on the negative side at t equals 6 seconds, at which time it's brought back to equilibrium, and then it just stays there. So this particle doesn't experience any disturbance until t equals 0, and it's done being disturbed at t equals 6. So clearly, the wave pulse is limited in space, and it passes through this one location, x equals 0, in a time of 6 seconds. So you could say that the pulse width in time is 6 seconds. Now let's look at the fact that the wave is moving at 1 meter per second. It's also moving left. We're going to need that. If it's moving at 1 meter per second for 6 seconds, I'll write this down in a moment, but just use distance equals velocity times time. 1 meter per second times 6 seconds means that the wave has traveled 6 meters during those 6 seconds. And when I say the wave, maybe you should just pick a particular place on the wave, like the leading edge, the front edge. During those 6 seconds, the front edge will travel 6 meters. So I think we've established that the width of the pulse in space is 6 meters. The only reason for that coincidence, 6 seconds in time, 6 seconds or 6 meters in space, is because they chose such a simple speed, 1 meter per second. Here's my solution to the problem. And since I don't have access to a tablet or a Surface Pro, I have to resort to the ancient art of writing on a piece of paper. And you can see I botched a couple things along the way. Down here is the graph that was given in the problem. It's the displacement at x equals 0 as a function of time. So remember, in general, the displacement depends on two variables: where you are on the x-axis and the time that you're talking about. For the history graph, that particular graph was showing us what happens to the particle located at x equals 0. So we're evaluating the displacement always at x equals 0, but for any time. And the book showed us that the particle doesn't get disturbed until t equals 0, at which time it goes high, hangs out, dips down, etc. And we know that the wave is translating to the left at 1 meter per second. Now, here's just a rule that you can use. If the wave pulse is traveling to the left, then the overall shape of a history graph and a snapshot graph will be the same. There's no need to reflect. So I'm kind of jumping the gun here, but this is the solution to the problem. This is the actual snapshot graph at t equals 1 second. This is the shape of the pulse on the string as that pulse travels to the left. And hopefully you can see that a moment ago, since this is traveling left, a few seconds ago, this whole pulse was over here somewhere. So take this shape, put it over here, and get it moving to the left. And you can see that if I call this the leading edge and the trailing edge, as soon as the leading edge, it's over here, as soon as it reaches the origin, like, let me back up. When this pulse is over here, the particle at the origin right here has not yet been disturbed. The string is just flat right there because the pulse hasn't arrived yet. As soon as it arrives, hopefully you can tell from the shape that that particle will be forced to move up, stay high for a little bit, and then go down. So when the wave is traveling left, a history graph has the same shape as the displacement graph. It's only when the pulse is traveling to the right instead that you would have to flip everything. Imagine if this pulse were over here somewhere, moving right. It had not yet arrived at the origin. So this particle at the origin, that part of the string is flat. Nothing's happened yet. And as soon as what would be the leading edge now, this would now be the leading edge. As soon as it reaches the origin, the particle would be forced to immediately dive down like that, and then rise, then hang out, and then dip down again. So everything would be reversed in time, and this graph would be flipped. So there's a rule that you can use. If the wave pulse is traveling to the right, then a history graph will be kind of like the mirror image. It'll have the same shape as the snapshot graph, but flipped. If the pulse is traveling to the left, you don't have to worry about that. They've got the same shape. And if you're wondering what's the reason for that asymmetry between the two scenarios, it's due to it's a consequence of the way we draw our graphs. We like to think of the time axis as increasing in that direction. T increases to the right. So that choice is the reason for the asymmetry. Okay, so we've established one aspect of the answer here. We know because the wave is traveling to the left, a snapshot graph will have the same shape. However, the width may be different. And also we have to figure out where it starts. So the answer to where it starts comes from the fact that the wave speed is 1 meters per second. So remember, this history graph tells us what's happening at the origin in time. So it looks like the particle at x equals 0 didn't receive the pulse until t equals 0 seconds. So the leading edge in this picture, the leading edge at this time, I should say, not in this picture, but at this time, the graph tells us that the leading edge of the pulse has just now reached the origin. So where is the leading edge of the pulse 1 second later? Because remember this point right here, sorry, this point in time is t equals 0 seconds. So again, at t equals 0 seconds, the leading edge of the pulse has just reached the origin. So 1 second later, where is the leading edge? Well, if it's traveling at 1 meter per second and 1 second has passed between t equals 0 seconds and the time at which we draw this entire snapshot graph, then the time interval would be 1 second. It's only scooted, I should really say negative 1 meter per second for the velocity. It's now at position negative 1 meters, which is why I've drawn it like this. So during the 1 second that passes from this time right here, t equals 0, to the time at which we're supposed to draw the snapshot graph. Remember, a snapshot graph means at a particular time you take a picture. It's like freezing time, and you can look at what the whole string is doing at that time. So 1 second after t equals 0, we know that this pulse has traveled 1 meter to the left, and that's why the leading edge I've drawn at negative 1. Okay, so there's 2 out of the 3 pieces of information we need. Number 1, I said, was what's the shape? Do you have to flip it or not? You can just use the rule. Number 2, where is the leading edge of the pulse? And lastly, how much do we stretch this out in space? We can see that the width of the pulse in time was, I think, 6 meters. That doesn't necessarily mean that the width of the pulse in space is 6. Did I say meters down here? I should have said seconds. The time width of the pulse is 6 seconds. That means wherever you are on the string, when you finally feel that pulse, it's going to take 6 seconds to complete. So that doesn't mean that it's going to be 6 seconds in space. It depends on what the speed is. So I think I already mentioned this a moment ago, but we can do the same thing. Use this equation again. The total width of a moment ago I used this for how far the leading edge traveled in 1 second, but now I'm asking, what's the total width in space of the pulse? Well, if it's traveling at 1 meter per second, I'm using absolute values now, I guess, and it takes 6 seconds to pass 1 point on the x-axis, then it has to be 6 meters long. Is there a better way to explain that? Hopefully that's clear. It really is easier to understand if you can picture it, and that's asking a lot of your imagination. Let's see if we can check out a simulation that makes this a little easier to conceptualize. Now, before I do that, let me make one interesting observation. Remember, the wave equation on a string says that the acceleration of any particular particle vertically, the transverse acceleration, is proportional to the curvature. That's the second derivative with respect to position, the curvature at that point. Let's see if that holds true for this wave pulse, which is clearly not sinusoidal. What's the curvature in this flat top region? Well, it's not curved at all. So the curvature is 0. The right side is 0. And that tells us that the acceleration of all the particles, remember, this is a snapshot graph at a particular time. So all the particles in this region, since the curvature in that region is 0, each of those particles must have an acceleration of 0, which makes sense, right? Because as this section of the pulse travels through any particular place on the x-axis, like let's just pick the origin. This is at x equals 0. As this whole thing moves to the left, you can see that the particle right here, as it experiences this part of the pulse, doesn't move up or down. It's got no vertical acceleration. So this equation is obeyed in here. Now, what about here? A little more complicated here. The curvature is still 0. The slope is not 0, but the curvature is 0. So the right side of this equation is still 0 for every particle along this segment of the string. Is the left side 0? It would have to be. Well, maybe you can see that as this straight line segment passes through any particular place, let's go with x equals 3, it's going to be diving down at constant speed. So the velocity of the particle is not zero, but because the velocity is not changing as this segment of the string passes through, the acceleration is zero. So sure enough, 0 equals 0. The only place where things get funky is at these corners. And you all know from calculus, in calculus, we don't like sharp corners. It makes the derivative undefined. For instance, right here, if you look at the left side, the slope is 0. If you look at the right side, it's some negative number. So what exactly would be the acceleration? It's probably undefined or some kind of infinity there. But everywhere else, this equation holds true. Let's look at a simulation now. The best little simulation I could find to demonstrate the relationship between the snapshot graph and the history graph is, of course, on the page of Dr. Dan Russell. We've already looked at some of his stuff. I have yet to go through all of this, but I'd like to at some point because every one of these pages is pretty awesome. So I scrolled down to the acoustics and vibration animations, and specifically wave motion in space and time. That sounds promising. And there it is. There's an animation of the wave pulse traveling down a string. So this is like showing a graph of d of x and t. You see how the displacement depends on x and time. But when this restarts, focus your attention on the red dot. The red dot, let's say, is located at the origin, x equals 0. And this is the history graph for that dot. So this is like, in the problem we just did, this graph on the left is like the plot that was given. And you'll notice that it takes a few seconds. It looks like, what, 10 seconds before the pulse is actually disturbed. So we start the clock now. Nothing happens, nothing happens. Now the pulse, or the particle is disturbed. I should have said the particle is disturbed. And then after the pulse finishes passing through, again, the particle is just hanging out at equilibrium. So notice there's no disturbance at, it looks like, okay, not the origin. They assigned the coordinate 10.25 to this point because I guess on the left side would be the origin. You've probably already figured this out, but just watch that. Okay. Nothing happens on the history graph until the pulse reaches the particle at 10.25. And let me draw your attention to the fact that the shape of this pulse in space, see how the very rightmost hump goes up and the leftmost hump is down? The history graph is the opposite of that. I wish I could pause the simulation here, but they are going to show you down here. Here's the snapshot graph. Do you see the connection between these two? They are flipped. For the history graph, on the very left, that hump goes up. On the snapshot graph, the hump goes down. Why? Because this wave is moving to the right. That was the rule I discussed in the problem. So if it's not sinking in yet, I guess just spend some time staring at these simulations. Next up, number 12. Oh, thank goodness we don't have to draw anything for this problem. They tell us how the displacement of a wave depends on position and time. Yes, they're using the variable y instead of x, but that's trivial. Just whatever your string is, if you want to think of this wave as a disturbance on a string, the direction of the string, call that the y-axis. Or if this is a sound wave, the direction of the wave that you're looking at, call that the y-axis. And we're supposed to, from this function, determine the frequency, wavelength, and speed. Easy. This is just a straight up application of all the little formulas we've been dealing with since the semester started. I have rewritten the function here. It's barely legible, but you can read it. The number in front of time here is 72. The number in front of y is 5.5, and then out front 5.2 centimeters. Maybe you're wondering, how come this quantity gets units and these quantities don't? Well, remember, I guess I'll just give this away right now. The quantity in front of the space variable, in this case, it's y, not x. That's what we call k. K has units of inverse meters, and y has units of meters. So inverse meters times meters is dimensionless. Remember, everything that you plug into the parentheses of a trig function, overall, that quantity has to be dimensionless. That's why there's no need to write the units here. But out front, the displacement that we're talking about is a displacement in space. It's got dimensions of length. So we actually need to write the centimeters. If we were talking about an electromagnetic wave, then the thing that's waving actually isn't any material object that's moving in space. It's something more abstract. It's the electric field that's oscillating. So the dimensions here would actually be, what is it, volts per meter or newtons per coulomb. Totally different dimension than a length. Okay, well, let's just compare that to the general formula for our progressive waves, progressive sinusoidal waves. We've got an amplitude out front and then a cosine or a sine, it doesn't really matter, of kx minus omega t. And if I wanted, I could add that phase shift, but since there's evidently no phase shift here, I'll just leave that out. So we just make these identifications. The wave number evidently is, there's that number, or that word evidently again, 5.5, and that's inverse meters. And we can just read off, oops, let me change this to a plus sign. So this is a wave that's traveling to the right. The angular frequency, we just read right off the function, is 72. And remember, that's radians per second, which is really just inverse seconds because the radian is a dimensionless quantity. And the amplitude, that couldn't be easier. They're not actually asking, however, for those three quantities. I think they do ask for the amplitude directly, but what they'd like to know is the frequency. Okay, what's the frequency in Hertz? So the number of cycles per second. There's a couple ways to go about this probably. Why don't we pick the most obvious one, which is the relationship between omega and frequency. So angular frequency is in radians per second. If you divide by 2 pi, that gives you frequency in cycles per second. Remember that tip I gave you about how omega is always the bigger number because you go through more radians per second than you do cycles per second. So it makes sense that we have to divide by 2 pi to get F. Okay, so the frequency in Hertz would be simply 72 radians per second divided by 2 divided by pi, 11.46. I don't need to keep all those digits, do I? They only gave us 2. And I'll write this as, it's actually unitless. That's what's strange about frequency. No, it's got units of inverse seconds as well. Yes. Have I ever really thought about this? Why do we write Hertz instead of inverse seconds? Maybe because inverse seconds are typical of omega. Yeah, that must be why we do that. I mean, strictly speaking, the dimensionality of F and omega are the same. In both cases, it's something per second. Radians per second is a dimensionless radians per second, and cycles per second is dimensionless cycles per second. So we must write Hertz to distinguish between cycles per second and radians per second. Okay. If you're curious, like I once picked up some old radio transceivers. I think they were from the 60s, and on the back, it gave the transmitting frequency, and it didn't give it in Hertz. It said CCS, or was that CPS, cycles per second? I forget, but it was back before everybody started using Hertz. Okay, so we've got that number. You can just round that to 11.5. And now they'd like to know the wavelength. The easiest way to do that would be lambda equals 2 pi over k. Because remember, lambda, k times lambda has to equal 2 pi. It's the same type of relationship as omega times period has to equal 2 pi. Just memorize, wavelength and wave number are reciprocals with the factor of 2 pi in there. So 2 times pi divided by k, we read the value of k right off the function, divided by 5.5, and the wavelength is 1.14 meters. And lastly, oh, I guess that was part B. I'll use the same piece of paper here. They would like to know the wave speed. Of course they would. I would go with this one. Speed equals wavelength times frequency. Count how many waves go by per second, multiply by how long each wave is. That's the total number of meters per second flying by. So if I take 1.14 meters and I multiply by, that's the length of each wave, and there are this many going by every second. Evidently 13.06, I'll just round that to 13.1 meters per second go by every second. I say evidently too often. See, I used to abuse the word apparently, and I got so irritated with it. I thought I got to find an alternative. So I switched over to evidently. Now I say that too much. There's another way to do this. Here's the second relationship. This wave speed is also omega over k. That's another one that I have memorized. Of course, it's equivalent because you could turn omega into f and you could turn k into lambda. Let's try that. Omega is 72. If I divide by k, that's 5.5. Yeah, of course, I get the same number. It's a good check. If you got different numbers, that would indicate that one of your calculations was in error. Number 14, and it's another super easy one. We're given a graph and we're asked to find three quantities: amplitude, frequency, and wavelength. One of these requires no calculation, and the other two just a little bit. So let's start with the amplitude. Well, are we looking at a snapshot or history graph? They're telling us this is a history graph for the particle at the origin. So this is what the particle is doing in time. When the clock starts at t equals 0, our particle dives down, then back up. But it's oscillating between, it looks like 6 centimeters high and 6 centimeters low. Well, we've already answered the first question. The amplitude is 6 centimeters. So I'm writing that down. And the frequency, can we determine the frequency directly from the graph? Kind of, because the frequency is how quickly it wiggles or shakes, oscillates, whatever word you want to use, how quickly it does that in time. So we just look at the graph. And what we can do is actually determine the period. How much time does it take to oscillate once? Well, this graph is shifted. It's neither a pure cosine or a pure sine. So let's just pick an easy point. Like you'll notice that the trough here lines up exactly with 0.2. So from trough to trough or valley to valley, 0.2 to 0.8 seconds. Just subtract those two, and it takes 0.6 seconds for this particle to oscillate once. That's the period of the oscillation. So I'm writing that down. The period is 0.6 seconds. In a moment, we'll turn that into frequency. When they ask about the wavelength, well, if this was a graph of displacement versus position, if this horizontal axis was x in meters, then we could just read that off of the graph like I just did for the period. But that's not what this graph is. So we're going to have to use some other means to determine that. And we do need this information. The wave is traveling at 2 meters per second. We don't actually need the fact that it moves left, but I'll keep that anyway. But I'm also writing that down. The speed is 2 meters per second. So I've written down the information that we just determined. The particle oscillated between 6 centimeters high and 6 low. It took 0.6 seconds to oscillate once, and the speed of the wave is 2.0 to the left. I suppose I could have just put a negative sign, right? A velocity of -2. Okay, amplitude, check. We already did that. What about the frequency? There's a very simple relationship between frequency and period. I like to use that stupid example. If it only takes you, or if you can blink your eyes 4 times a second, then it only takes you 1/4 of a second to blink your eyes once. So those are reciprocals. 0.6. I don't feel like reaching for my calculator right now. So let's do it this way. That's 1 over, well, this is 6/10, right? And 6/10 is the same as 3/5. All right, so take the reciprocal of that. That's 5/3. 3 goes into 5 one time with 2 left over. 2/3 is like 0.66. So I'll call it 1.67 Hertz. And there it is. So this particle oscillates 1 2/3 of a cycle every second. So almost 2 times a second, more than 1 time per second. There's the frequency. Wavelength, again, we were not able to read that off the graph, so we're going to have to use one of our formulas. There's this one, speed equals frequency times wavelength. Aha, we know the speed, we know the frequency, we can solve for lambda. Or there's this one, omega over k equals v. The problem with that is, well, that's not going to help us because we're looking for lambda, not k. I mean, once we know lambda, we could find k. Let's not do it that way. Besides, we don't even know omega directly. We'd have to take the frequency and divide it. No, multiply it. We'd have to multiply f by 2 pi to get omega. So let's just take the path of least resistance. Lambda would be the 2.0 meters per second divided by 1.67. And here I will write the frequency as having dimensions of inverse seconds. So we see that the seconds cancel. You know what? I'm not going to insult your intelligence. You know how to divide two numbers in a calculator. That's how you manipulate our formulas. This next problem requires us to use a quantity which has not been discussed in this class, and you likely did not see it in a previous class. We have to use this quantity called the bulk modulus, which tells you the elasticity of a liquid or a solid. We're supposed to be calculating the speed of a wave in Mercury, which, as you know, is a liquid under normal conditions. So for transverse waves on a string, this was the appropriate formula where that's the mass density, transverse string. But for a solid or liquid, it looks a little different. This is for longitudinal waves, longitudinal on solids or in solids and liquids, because there are other types of waves possible. I think you can have transverse waves in a solid, unless there's no shear forces. Okay, so remember, T tells you something about the elasticity of the medium, and so the bulk modulus, capital B, must do the same. It's basically how springy the material is, the medium. And instead of linear mass density, this is the volume mass density. The units here are kilograms per cubic meter. And I forget the units for bulk modulus, but I'll find out in just a second when we review the definition. So let me point out now, you will not have to understand or use the definition of the bulk modulus on your exam. If you're provided the bulk modulus for a particular material, you may be asked to use it in a formula like this, but you don't have to understand the definition of bulk modulus. That's not really part of the curriculum here, but we need to go through it anyway right now. So recall Hooke's law for a spring, an ideal spring. The force which you must apply, the spring force that you have to apply, is proportional to the amount by which you want to stretch the string. And that constant of proportionality we typically call K. So the harder you pull or push on the spring, the greater the displacement that results. Another way to think about it is, suppose you know the desired stretch. If you know how much you'd like to stretch it, this constant of proportionality tells you how much you will subsequently have to pull on it. Okay, so for the purposes of relating this to the bulk modulus, I want to call this, instead of a displacement of the spring, let's call it a strain. When you strain a material, you deform it from its equilibrium shape. So I'll call this strain. And instead of calling this force, which is what it is, let's think of it as a stress. When you apply a force to the spring, you stress it. And you know what, let me put these in quotes because these are actually not, they don't have the dimensions of strain and stress. So I'm saying these are like stress and like strain. And this is some measure of the elasticity of the spring. Some measure of elasticity. Okay, because we can make a direct analogy between this statement and another statement. excuse me, suppose that instead of trying to stretch an ideal spring, we were trying to, let's say, compress a volume of fluid. So here's a bubble of fluid. Maybe it's actually a cylindrical segment of, or a volume of fluid inside a cylinder, and you're trying to compress it with a piston. I'll just go with this shape. So if this is the original shape, volume V, or maybe I should call it V naught. No, I'll just call it V. And if you'd like to squish it, you're going to have to apply pressure all over the surface, really an increase in pressure, because most things, most of the time, are immersed in some kind of pressure anyway. Anything that sits out in the open is being subjected to atmospheric pressure. So V is the volume that it already has when it's subjected to its normal pressure. If you'd like to squeeze it into a smaller volume, you have to apply an additional pressure. And you could call that delta P. Some books just call it P, where P is the extra pressure. For now, I'll call it delta P. That's not really legible. Okay, so I'm going to apply an extra little bit of pressure beyond atmospheric pressure, let's say. And as a result, let's say the whole thing gets compressed. How about I outline this? So the bold line is the original volume, and it's going to be compressed into some smaller volume. Maybe I should make that dotted. Okay, so the dotted outline shows the new volume, and this is way exaggerated. Most solids and liquids cannot be compressed that much. And this shaded portion here is the amount by which the volume decreases. So let me draw an arrow pointing to that shell of removed volume, I could say. So that's delta V. Delta V is the volume of this shell by which we've moved inwards. And let's look now at the fractional change in volume. Like, did we now just compress it by 1%, 1,000th? That's this quantity, the change in volume compared to the original volume. If this ratio is 0.01, that would indicate a 1% change in volume. Obviously, the greater the percent change in volume that you'd like to achieve, the greater the pressure you're going to have to apply. So this increase in pressure here is going to be proportional to the percent change in volume. If you'd like to compress this thing by 2%, you're going to have to subject it to an increase in pressure that's twice as great as it was for 1%. Seems pretty intuitive, right? So why don't we just replace this statement of proportionality with an equal sign? And the constant of proportionality, just like we went with a K for spring constant here, we go with a capital B, and it's called the bulk modulus, which to me sounds like a superhero. That's the bulk modulus. And I believe we actually can call this the strain. The percent change in volume could be called strain. I think this, I'm going to say, is like stress. It's not really stress because it has units of pressure, newtons per square meter. But if we solve for beta, I'm killing a lot of trees here. The bulk modulus, by definition, just solve this for beta. And now instead of delta P, again, depends which book you're looking at, let's just use the letter P where it's understood. P is the extra pressure that you have to subject the material to. That's all it is. It's the pressure required compared to the fractional change in volume. And there's one subtlety. If you apply extra pressure, if P is positive, isn't the change in volume negative, right? It's decreasing in volume. But we'd like the bulk modulus to be just a positive number to describe how springy the material is. Obviously, the harder it is, the springier those interactions are between particles, the bigger this number would be. So we stick a minus sign out front. The minus sign, again, is just because of the opposite sign between the added pressure and the change in volume. Okay? So the more pressure it takes for a given fractional change in volume for a bigger strain, or for a given strain, I should say, the greater the bulk modulus is. So the greater the numerator is for a given strain, clearly, the greater the bulk modulus is. And why don't we look at a table of bulk moduli? Before I do that, look at the units here. The units of pressure are, of course, newtons per square meter, kind of like pounds per square inch. And you may not have seen that a whole lot in your previous classes. And down here, we just have a dimensionless quantity, right? Cubic meters over cubic meters. So the units of the bulk modulus are really the same as the units of pressure. In other words, the Pascal. A Newton per square meter is called a Pascal. For a point of reference, the atmospheric pressure at sea level and regular temperature is 100,000 pascals. So 10 to the fifth pascals roughly is 1 atmosphere. So a Pascal is a pretty small unit of pressure. Now, for, excuse me, if you're talking about a strain of 1,000th, I'll go with the absolute value, 0.001. If you'd like to decrease the volume by 1 part per thousand, let me plug that in here and then solve for P. The pressure required would be negative delta V over V times the bulk modulus, which is 0.001 times the bulk modulus, because I'm imagining a fractional change of 1 part per thousand. And I'm telling you that so that in a moment, when I pull up a table of bulk moduli, we can take the bulk moduli, multiply them by 1,000th, and then that will tell us how much extra pressure is required to compress something by 1 part per thousand. And that makes those numbers easier to appreciate. And keep in mind what a Pascal is. 1 atmosphere is 10 to the fifth pascals. So we're going to see that the pressure required to achieve even a 1 part per thousand decrease in volume is much greater than 1 atmosphere, which tells us that most liquids and solids are not easily compressed. I just pulled this off the web. One of the numbers on here we're actually going to use in a moment. Right, they're telling us right here that Mercury has a bulk modulus of 2.5 billion. And you'll notice the units here, newtons per square meter. That's the same as a Pascal. Okay, so let's use the device I just introduced. Let's take one of these numbers. Do they give us the bulk modulus of water? Yes. I think most of us have a sense that it's difficult to compress water. 2 billion, that's the bulk modulus. So multiply that by 1,000th, 0.001, and you get 2 million, okay? So that tells us if you'd like to take a volume of water, put it in a cylinder with a piston, and shrink it by 1 part per thousand, you're going to have to apply 2 million extra pascals of pressure everywhere on the surface of that water. 2 million, well, 100,000 is 1 atmosphere. So that's like, what is that, 20 atmospheres? I think I'm doing that right. That's incredible. 20 atmospheres of pressure are required just to compress the volume of water by 1 part per thousand, 0.1%. That's what these numbers tell us. Okay, so I'm going to write down the bulk modulus of Mercury, which is what we need to solve this problem. Capital B for Mercury, Hg, is 2.5 billion. And your solutions manual, just to make sure this is the correct value of the bulk modulus, I'll compare my answer with what the solutions manual gets, because you can also find the bulk modulus of Mercury somewhere in your book. The problem itself gives us the density of Mercury, 13,600 kilograms per cubic meter. For comparison, of course, water has a density of 1,000 kilograms per cubic meter. So Mercury is almost 14 times as dense as water, which is amazing. That means if you had a 1 liter bottle and you dumped out your Pepsi or whatever, and you filled it up with liquid mercury and then drank it, no, don't do that. It would feel as heavy, almost as heavy as 14 bottles of water. That's really hard to imagine. Okay, now that we've got the numbers, we just plug them in. How quickly does a longitudinal wave travel through liquid mercury? I'm going to suppress the units. We'll just trust that they all work out and it comes out in meters per second. You do need to plug in SI. Like don't be converting this to grams per cubic centimeter, which would be 13.6. 2.5 billion divided by 13,600 equals, take the square root. What? That can't be right, because I know that I'm getting 429 meters per second, which is not much faster than the speed of sound in air. And I know that sound waves travel way faster in solids and liquids. So am I doing something wrong? 2.5 billion divided by 13,600. Take the square root. Okay, so the value that I took from the web doesn't seem right. Let me figure out what I did wrong. And the book is reporting a different number. The book is reporting 2.85 times 10 to the 10th. So more than 10 times greater. That's what I get for just pulling a number off the web randomly. And if we use that value for the bulk modulus of Mercury, then we find a much greater speed of, I'll round it to 1448 meters per second. Whoa. Remember, at room temperature, sound waves travel at something like 340, 343 meters per second. So this is what, 5 times greater than that, roughly? Sound generally travels much quicker in liquids and solids. In fact, I think I was just rereading the chapter, and there's some common medium like steel in which, or I think it was rock, maybe. Sound waves travel almost as fast as the ISS orbits planet Earth. It's almost at orbital speed, so that's remarkable. And I want to emphasize, this is only for longitudinal waves. Those of you who have taken geology or know a thing or two about this, I really don't. There are multiple types of waves that can travel through the Earth. There's different types of seismic waves. There's the P waves, the S waves, and then Dr. Dan Russell's page talks about Rayleigh surface waves. Those waves all have different speeds. So this formula, the square root of, where's the formula? Root bulk modulus over volume mass density, that's only applicable for longitudinal waves. You would use some different type of parameter up here if you were talking about a different type of wave. And for that, you're going to have to study something called the stress tensor. Those of you who major in civil engineering and mechanical engineering, I think you'll probably encounter that. Number 16.30, number 30. Very simple as far as the math is concerned, but the concept is extremely important. This will get used a lot in chapter 17 and the chapters on interference and diffraction. So can't emphasize this problem enough. In this problem, we're dealing with spherical waves. So think of that trumpet emitting a continuous tone, except a trumpet really focuses its power in the direction of the bell. So this is an isotropic source of sound. The intensity would be the same everywhere across one of these spherical wavefronts. And these are all moving outwards at the wave speed v. And remember, when we draw something like this, the circles correspond to, let's say, the peaks in the intensity, or the displacement, really, if we're talking about like that pressure wave. These are the peaks in the displacement, and then I could draw a dotted circle halfway to the next peak. That would be the valley. So if you pick a particular direction from the source, call that the R axis, and then you plot the displacement. So this is a snapshot graph. Freeze time. Oops. And then you plot the displacement versus distance r from the origin. It would look something like this. So some of the air particles have maximum displacement. Some are not displaced at all. Some are displaced in the opposite direction. It's a little abstract, isn't it, to go from this to that? And that's why if we're told that the wavelength is 2 meters, as we are in the problem, it makes sense to label this distance 2 meters, because this is the peak to peak distance right here. The wavelength is 2 meters. That's supposed to be a 2 right there. And then what they tell us is at a particular distance from the source. And I should point out, let me start with this graph. This is a sine or a cosine that's been shifted. And we know that if you pick any arbitrary point on a sine or cosine, you have to move the argument of that function or the phase through 2 pi radians to move one wavelength. So the phase changes by 2 pi radians as we go from here to here. Or we could start here and end here. If you start here and end here, you've also moved the argument of your function through 2 pi radians, also known as the phase. You've moved the phase through 2 pi radians. So they tell us that at a particular distance from the origin equal to 4 meters. So let me draw, I'm going to call this the 4 meters. That's an M for meters. And this is a little, this is a little misleading because if this is 2 meters and you count out from the source, 4 meters would be somewhere over here, right? That's actually not important to the outcome of this problem. So just forget about that. Don't worry about that. They're telling us that the phase here is pi radians. And that's why I chose to put 4 meters right here, because I'm going to say that the peaks here, let's call this phase 0. I guess we would be talking about like a cosine function because cosine of 0 is 1. So here the phase is 0. The phase here then would be 2 pi radians. The phase here would be 4 pi. This is really sloppy. So every time you advance from one peak to the next, you've advanced the phase by 2 pi radians. So if the first one has a phase of 0, then this has a phase of 2 pi, 4 pi, etc. So on this picture, presumably this would be this wavefront that's just now leaving the source has a phase of 0 radians. Whoops, I guess that ought to be this one. Let's call this the 0 radians phase. 0 radians, and then this would be 2 pi radians, and then this would be 4 pi radians. And that's why I chose to put r equals 4 right here, because we can see halfway between 0 radians and 2 pi radians would be pi radians. And what they're asking for now in number 30 is for the phase, by the way, this is also snapshot, because if we watch what happens in time, all of these wavefronts are radiating outwards. What is the phase at r equals 3.5 meters and 4.5? So what's the phase at r equals 3.5 meters and 4.5 meters? And we can actually answer this without writing anything down or doing any calculation on paper. We'll go back and do that as well because we need to know how to do that. Remember, a wavelength is 2 meters, right? And we're right in the middle between two peaks. So I've added some things to the drawing here. If the wavelength here between peak to peak is 2 meters, and at the midpoint, I'm calling that 4 meters from the origin, then every point on this wavefront would have to be 3 meters from the source, and every point on this wavefront would have to be 5 meters from the source. So from 3 to 5 meters, that is 2 meters, and the halfway point would be 4 meters. And in keeping with this drawing, I'm just choosing to say that the phase on this circle is 0 radians, and then the next peak, or the next wavefront, moving from here to here, would have a phase of 2 pi radians. That's why the midpoint has pi radians. So if we're at a distance of 3.5 meters, what would the phase have to be there? Well, if this is 3 meters from the source and this is 4 meters, 3.5 meters would be right here in the middle. And you can see that's halfway between a phase of 0 and a phase of pi. So evidently, the phase right here, if I want to draw that wavefront, this is at 3.5 meters, the dotted line here. That would have to be a phase of pi over 2. And we could see that also in this graph. If this is phase 0, this point right here would correspond to a phase of pi. And that means this right here would correspond to a phase of pi over 2. Maybe this is not so clear to you. What about 4.5 meters? So halfway from 4 meters to 5 meters. Well, if we go from a phase of pi here to a phase of 2 pi on this wavefront, what's halfway between pi and 2 pi? That would have to be 3 pi over 2. Okay, let's do it with math now. Here's the formula that we will definitely be using repeatedly. All you have to do is take the displacement in space, which would be R2 minus R1. Compare that to a wavelength. And that is your phase difference. So we'll call that the change in phase difference. Think about it. If you've scooted outwards by one full wavelength, like if you start on this wavefront and you move out to here, since you've scooted by one wavelength, then the phase has changed by 2 pi radians, right? On this picture, every time you scoot by one wavelength, your phase is increased by 2 pi radians. So the last thing is you have to multiply by 2 pi. Let me rewrite that down here. The phase difference, which is defined as the phase at location 2 minus the phase at location 1, you take the ratio of the change in position over wavelength, and you multiply that by 2 pi radians. You take this fraction of 2 pi. So the example I was going with just now, if you go from one wavefront to the next, then your delta R, you've scooted out by one full wavelength. So the numerator would be lambda, 1 lambda. Well, lambda over lambda is 1. 1 times 2 pi is 2 pi. Do you see that? On the other hand, if you had only scooted out, let's say you went from here to halfway, that's a scoot of only half a wavelength. I didn't go all the way to the next wavefront. So half a wavelength for delta R would be 1/2 lambda. When you divide by lambda, you're left with 1/2. 1/2 times 2 pi is pi. So if you just go half a wavelength, scoot from here to here, your phase shift has been pi radians. That'll take you from a peak to a valley. Okay, so this is the equation that we're going to use an awful lot in the coming chapters. If you'd like to know the phase difference between 2 points at a given time, that's key. You've frozen time. The phase difference between 2 points, all you have to do is take the change in position along that axis, compare it to the wavelength, and then take that ratio or take that fraction of 2 pi. That's the phase difference. So we can use that formula to solve this problem now. So let's say that the phase, I'll call it delta phi. That's the phase at R equals 3.5 meters minus the phase at R equals 4 meters. Okay, so I'd like to know the change in the phase. Well, that would be 3.5 meters. This is the delta R minus 4 meters compared to the wavelength of 2 meters. So this is delta R over lambda. And we take that fraction of 2 pi. Well, 3.5 minus 4 is negative 1/2. So negative 0.5 over 2 times 2 pi. Well, that's negative 1/4, is it not? And 1/4 of 2 pi is pi over 2. Yes, so negative pi over 2. Okay, so look at the far left and far right of this equation. I'm trying to show you multiple ways to think about this. If you solve for the phase at 3.5 meters, let me just do that. Phi sub 3.5, I'll call it that now. I can scoot this to the other side now. That would be phi sub 4.0 meters minus pi over 2, which is pi radians. Remember, we were told that the phase at 4 meters is pi radians minus pi over 2, and of course, pi over 2. So we get the same answer that I got just by thinking through it conceptually. There's another way to do it as well. Remember, one full wavelength corresponds to 2 pi radians. Half a wavelength, if you go from here to here, half a wavelength would just then be pi radians, and a quarter of a wavelength, does everybody see that? This is a quarter of a wavelength, half a wavelength, a full wavelength. I know this is review for a lot of you, but that's half a wavelength. This right there would be a quarter of a wavelength. So phase difference of 2 pi, phase difference of pi, phase difference of pi over 2. How many wavelengths are we scooting here? This is a full wavelength, 2 meters. If we're scooting from 4 meters to 3.5, well, that would be half a wavelength. So we've really just scooted a quarter wavelength. So there's your answer right there. If you scoot a quarter wavelength towards the source or away from the source, your phase is just going to change by pi over 2. That's probably the easiest way to think about it. I would just memorize that. If you scoot a full wavelength in either direction, your phase will increase or decrease by 2 pi radians. If you scoot a half a wavelength, so from here to here or here to here, half a wavelength in either direction is pi radians phase change. And if you only scoot by a quarter of a wavelength, you're talking about pi over 2 change in phase. That's it. So now we can just recognize that if we go from 4 meters to 4.5 meters, that's going to be an increase of pi over 2. So we would go from pi to pi plus pi over 2, which is 3 pi over 2. Couple different ways of getting to the same result. You definitely want to know the formula. Where did I put it? I'll just rewrite it. Phase change at a fixed moment in time. You take the change in position, divide by the wavelength, and multiply that by 2 pi. Hopefully that's intuitive. Later, we're going to call this the path length difference when we talk about interference. Okay, that picture was crap. So here's a better one. You've got the bold concentric circles representing the spherical wave fronts where the displacement is maximum. So the wavelength obviously is the distance between 2 consecutive wave fronts. That's the 2 meters. And I've drawn wave fronts, 3 consecutive wave fronts with corresponding phases of 0 radians, 2 pi radians, and 4 pi radians. And we're told that at a distance of 4 meters from the source, we're at a distance where the phase is pi. So we're halfway between 0 radians as the phase and 2 pi. So if these are the peaks, these would be the valleys, so to speak. And again, I know that this distance from the origin would not actually be 4 if this were 2, but there's a way of correcting the picture. That's non-essential. And so we're supposed to find the phase anywhere on this dotted yellow circle or dashed yellow circle, which is 3.5 meters, right? Like if this distance is 2 meters right here, and we're currently right here, if we back up by this much, well, wouldn't this be 1 meter? See the distance I'm indicating? This is 1 meter, so this would be half a meter. So if we back up by half a meter from 4, that puts us at 3.5 meters. This would be 3.5 meters from the origin. And what's the phase? You can just read it off the picture. If this circle everywhere has a phase of pi, and this circle has a phase everywhere of 0, then halfway between would have to be pi over 2. On the other hand, if we move outward by half a meter, that brings us here to 4.5 meters. And again, we've moved halfway between the pi radians valley and the 2 pi radians peak. So that would have to be 3.5 or 3 halves pi. What is that? What's the number halfway between 1 and 2? 1.5. 1.5 pi is the same as 3 halves pi. Okay, I hope that helps. Numero 40, also known as number 40. With this one, we can get some practice with the Doppler sound level scale. So we're told that a power saw has a sound level of 100 decibels. That's pretty loud. That could cause hearing damage over a duration. And that's how loud it is when you're standing 5 meters from it. So how far do you have to go to bring that sound level down to 80 decibels? I bet you we could do this right now verbally without writing anything down if we remember a couple things. Number one, easy rule. Every time you scale up the intensity, that's the SI intensity in watts per square meter, by a factor of 10, that corresponds to an increase in the decibel level of plus 10. See that? So a multiplicative relationship gets turned into an additive relationship. So 10 times the intensity means 10 decibels louder. Conversely, 1/10 the intensity means you've dropped down by 10 decibels. So if we want to drop from 100 to 80 decibels, we have to multiply by 1/10 twice, or the intensity needs to be cut down by a factor of 10 twice. So we're talking about an intensity at some distance, some desired distance, that's 1/100th the intensity of the sound level at 5 meters. Now, do you recall that for an isotropic radiator where we don't have to worry about reflections and absorption, the intensity falls off like 1 over r squared. It's an inverse square law. So how far out do you have to go to bring the intensity down to 1/100th of its original value? Inverse square law tells us that 10 times the distance, 1 over 10 squared, that will give us 1/100th the intensity. So there it is. We already answered the problem. We have to be 10 times as far away, which brings us from 5 meters to 50 meters. Now, I guess we'll write some stuff down on paper to make that a little more concrete. Because let's face it, that's not going to fly on an exam, right? You can't just think it out loud and not write anything. What am I supposed to grade? So I will start by reminding you of the definition of the sound level in decibels. You've got this factor of 10 out front. You take the log base 10 of any intensity compared to our reference intensity of a trillionth of a watt per square meter. And that means that the difference in two sound levels, beta 2 minus beta 1, we would have this expression for intensity I2 minus this expression for intensity I1. They both have this factor of 10 decibels out front. So let me factor that out. The log of intensity 2 compared to reference intensity minus the same expression for intensity 1. And here's where we use the rule where the difference in two logs is the log of the quotient. So we can rewrite this as the log of I didn't really need these brackets, I2 over I1. The I naughts will cancel when you take the quotient. There it is. So change in decibel level is 10 dBs log of I2 over I1. So if we have a delta B of negative 20, because remember, in this problem, currently the power saw at 5 meters is 100 decibels, and we'd like to bring that sound down to 80. So we need a decrease of negative 20. So if we plug this in here, we've got a negative 20 and a 10. Can't we just divide both sides by 10 and turn the left side into negative 2? So negative 2 equals the log of I2 over I1. And how do we get rid of that log base 10? Remember, the inverse function of the log function is the anti-log. So we will exponentiate both sides. That means take the number 10 and raise it to both sides. Well, this, of course, is 1/100th. And 10 to the log base 10, those undo each other. And there it is. The ratio is 1/100th. To be extra clear, I2 is 1/100th of I1. That's not quite the answer to the question. We're supposed to figure out how much farther we need to go. So I'll remind you that the original distance was 5 meters. And then we remember the equation for how intensity depends on distance from the source, provided we don't have to worry about absorption, reflection, and directionality. So it's an isotropic radiator. You take the power and you just divide by the surface area of that sphere at radius r. All that power is distributed over that large spherical shell or surface. And that means that if we compare the intensity at distance 2 to the intensity at distance 1, you can see the p's will cancel, the 4 pi's will cancel, and we'll have R1 squared over R2 squared. I need the equal sign, don't I? And we've already determined this ratio. What are we solving for? R2 in terms of R1. So R2 squared is equal to R1 squared times I2 over I1. Lastly, take the square rootify it, take the tooth root, as I like to call it. So you know how we call this the third root of x? I like to call this the tooth root of x, commonly known as the square root. Okay, so when we take the square root, this just becomes R1, and the ratio of the intensities is under the radical, and that's the 5 meters. Wait a minute. Aha, I forgot to reciprocate, right? When I solve for R2 and I put this ratio on the other side, the subscripts are opposite. Yeah, so this is intensity 1 compared to intensity 2. We need that because we're supposed to be scaling up from 5 meters. Sorry, this is meters. We're supposed to be scaling up from 5 meters to 50 meters. So I1 over I2 is 100 to 1. Square root of 100 is 10. There it is. Ain't nothing but a thing. Number 41 is a Doppler effect problem, Doppler effect for sound waves. The problem did not assign names to the participants, so I've taken the liberty of calling the dude on the skateboard here Billy, and Gene is seated. We're told that Billy is moving towards Gene at 25 meters per second. It says racing towards Gene. Well, that's over 50 miles an hour, so I'm pretty sure Billy's not running that fast. So I put him on an electric skateboard, and we're told that he is singing a pure tone, 400 hertz. That's in his frame of reference, of course. And in part A, we're supposed to figure out what pitch does Gene hear. Now, again, I took the liberty of writing F plus because it seems clear that the frequency that she hears will be higher than the source frequency, because remember, when a source is in motion producing waves through a medium, again, we're not talking about electromagnetic waves, which are different. Billy is producing waves that travel through a medium, the medium being air. So we know that the wave fronts will bunch up in front of him, and they'll spread out behind him, or you could say they're compressed in front, spread out in back. The wavelength gets shorter, but the speed of the waves doesn't change. That's an important point. You can't change the speed at which the ripples travel through the air. That's a property of the air. So if they're all bunched up closer together, but they're still traveling at the same speed, you can see why they would be hitting Gene's eardrum more often. Yeah, sorry about the goofy heads here. I didn't get my master's in drawing, did I? So part A, what is F plus? Well, here's my advice. Remember, when you're trying to decide whether you put the, you've got this possibility, 1 plus velocity of the observer over velocity of the source times the emitted frequency, or this one, F naught over 1 minus V. Oh, that's supposed to be just V. This is the speed of the wave through the medium. Both of these formulas would produce an F plus that's higher than the emitted frequency. This is obviously a number greater than 1, and the quantity in the denominator is less than 1, which makes the whole thing greater than F naught. When you're trying to decide, try to remember that point I made in a previous video about how if you look at the denominator, you can see that it's possible for this expression to shoot up towards infinity. It approaches an asymptote or there is an asymptote at source velocity equals the speed of the wave through the medium. And you can only do that if the source is moving. Hopefully you'll just remember that if you've spent some time with the graphics in the book and the simulations that I presented. So we are talking about the source in motion. So this is the one to go with. Okay. 400 hertz is in the numerator, and down here we have minus source velocity compared to wave speed. Now, wait a minute. What are we supposed to do for the speed of the wave through the medium? Because the speed of air depends on temperature. Uh, in the problems presented in this chapter, we don't ever worry about the change in air pressure. In fact, I think your book shows within the chapter that the speed of sound does not depend on the pressure if you model air as being an ideal gas. And ideal gases are something we will take a close look at later in the semester. So do they give us the temperature here in number 40? No, 41. They actually just give us the speed of sound. So for future reference, when the temperature is 20 degrees Celsius, which is around room temperature, then the speed of sound is something like 343 meters per second. And there is a formula in your book, which I didn't take time to look at, that describes how the speed of sound depends on temperature. We'll probably look at that later in the semester. They just straight up tell us in this problem that the speed of the sound waves is 340. So we don't have to mess with determining that speed based on the temperature. Because like I said, there is a formula in the chapter for calculating sound speed in terms of temperature. Okay, just plug numbers in. What could be easier? 1 minus 25 compared to 340. I don't really need to write units because they would cancel anyway. So on my calculator, 1 minus 25 divided by 340, my calculator knows the order of operations. I hit equal first, then I take the reciprocal of that and multiply by 400. And Jean, that's the name I assigned her, she will, or is it Jeannie? She'll perceive a frequency of 432 hertz. So Billy may be emitting 400 wave fronts per second, but because they're all bunched up due to his motion, 432 of them strike her ear every second. Now, those of you who have some music background may be wondering, is this enough to bend the pitch up by, let's say, a half step? If you've ever played a musical instrument, you know that Western music, at least, is based on the 12-tone scale. So going from an F to an F sharp, for instance, corresponds to an increase in frequency. Well, I'm going to make this very brief because it's not really part of our curriculum. But the middle C on a piano, I don't actually know. I'll call it middle A, has a frequency of 440 hertz. And the A above that, I'll call it A 1 octave above. Can you even read my writing? Is twice that, 880 hertz. So every time you go from one note on the keyboard, for instance, to the note 1 octave higher, like from A to A or B flat to B flat, you double the frequency. And so when you go up, if these are the keys on the piano, I'm going to embarrass myself here. Isn't there a note like right here? Yeah, I think I did that right. Okay, so as you go up one, I left one out. You get the idea. As you go up one note at a time on the keyboard, you're multiplying each frequency by a certain number. And since there are 12 tones, like F sharp would be some constant ratio times F. This represents the frequency of F sharp. And the frequency of A, for instance, would be some number times the frequency of A flat. We have to figure out what that number is. Well, we know that going up a half step 12 times will take you from one octave to the next. So A to the 12th power would have to be the ratio 2. Because when you go up 12 tones, you're now an octave higher than you were before. And we know that that octave higher is double the frequency of the original note. So whatever this ratio is between adjacent notes on the keyboard, in other words, a half step apart, that ratio to the 12th power would have to be 2. And that means that A is the 12th root of 2. Now, there are different ways to tune a piano, but one way is just to make sure that every note is that much higher than the previous one in terms of frequency. So if we take the 12th root of 2, that would be 2 raised to the 1 divided by order of operations. Let's see, 2 raised to the, in parentheses, 1 divided by 12, close parentheses. Okay, 1.059, that's right. You do not need to know this for your exam. I'm just adding a little extra info for those of you who might be interested. Okay, so in order for this pitch to sound 1 semitone higher to the listener, the frequency would need to be this factor higher. And let's see, where's my numbers? Here we go. 400 hertz. I'll multiply that by that ratio of 1.059. Okay. The frequency would need to be 424 hertz, basically, to sound 1 semitone higher. The received frequency is even higher than that. Okay, so there it is. Somebody playing or singing a very typical note in the middle of the scale, somewhat in the middle of the human voice. If they're moving at 50, 60 miles per hour, the person listening would hear that tone half a semitone higher, as they call it in music. Cool. Now this problem really isn't difficult because you only have to use the formula once. I guess we should do part B now. Okay, in part B, now Jean is singing, and what frequency is she singing? Also 400 hertz. So now she's the source. This is really sloppy. Let me put it down here. So F naught over here is now 400 hertz. She's a stationary source. That's different from before. Previously, the source was moving, so the wave fronts were all bunched up. Now the source is stationary. We don't care if he's singing or not now. We're just interested in what he hears as he approaches Jeannie. She's singing at 400 hertz. What does Billy hear? Well, this is a case of a moving observer. So now I really need to change this V sub S to a V sub O for speed of the observer. And we know that because he's cutting through the waves, all of these wave fronts are moving away from Jeannie's head at 340 meters per second. But because he's moving in the opposite direction at 25, these wave fronts appear to be passing him at 365 meters per second. And that's the origin of that Doppler shift here. So we use the other formula. The upshifted frequency now is 1 plus V observer over V of the waves times F of the source. And let me just do this all in one shot on the calculator. So if I take his speed of 25, excuse me, and I compare it to the wave speed of 340, then I add 1, and I get 1.07. I multiply that by the source frequency of 400. And you may have guessed that you get the same number, but no, you do not. This one's a little lower. So there again is a difference between this Doppler effect and the Doppler effect for E&M waves. If we were talking about electromagnetic waves, and you go back to my silly slides with Pablo Picasso and Nancy Pelosi, all that mattered was their relative velocity. It didn't matter who was doing the moving, because since there's no such thing as an ether, it's irrelevant who you think of as being at rest and who you think of as being moving. There is no absolute reference frame. There is no absolutely at rest person. All that matters is the relative speed. There's no distinction. But here we actually find that it does matter whether the source is moving or the observer is moving. You get two different frequencies depending on those two cases. They're close. So this problem is still, even with part B, it's not particularly difficult. There's a Doppler effect problem presented in the chapter that's more interesting. And I'll see if I can find the page number real quick. I'm sure you've already read it because you've already read this chapter a couple times, right? Well, the challenge problem on 448 is good, but also, here we go. Example 1611 on page 447. That was a more interesting problem because you have to do a little bit of clever algebra to get the result. Okay, moving on. This one's kind of fun. Number 51 is about the speed at which earthquake waves travels, or seismic waves. So suppose the epicenter is here. This is where, I don't know, some event happened with two plates of the Earth's crust moving past each other and they slipped and created this giant disturbance. And it takes a while for that disturbance to propagate outwards through the rock and metal of which the Earth is made. And I know that the speeds depend on the medium. So if it's traveling through the crust, that's going to be a different speed than if it travels through the mantle or the core. I don't know anything about that, but it's probably a really interesting subject. So there are two types of waves that are emitted. You've got, actually it's more than that, because remember there's the Rayleigh surface waves as well, but the P and the S waves, so-called, you've got your longitudinal waves, which I'm going to represent like this, and they travel faster. So this is the P wave. So during a given time interval, if the P wave has traveled this far, so it's almost reached this city here, the S waves travel slower. So I'm going to have it stop earlier, like it didn't make it quite as far. These two waves are going to arrive at different times. And I once read that if you're really observant, when an earthquake first starts, you can kind of tell when those two waves arrive. Like if you're looking at a light post or a lamp post, it might be doing this before it starts to do this. And, you know, you've probably heard that animals detect earthquakes before we do. A lot of animals have superior hearing to ours, or maybe they can hear low frequencies that we don't hear. Maybe they're picking up on one of those waves that's imperceptible to us. Okay. So primary and secondary, that helps if you think P waves arrive first and S waves arrive second, but I don't actually think that's where those letters come from. We're given the speeds of these waves. This was where that number came from. So 8,000 meters per second is roughly how fast satellites orbit the Earth in low Earth orbit. And that's how fast these P waves travel. Remarkable. Much faster than the speed of sound in air, right? More than 10 times faster, something like 20 times faster. And the velocity of the secondary waves, let's see, number 51, these travel at 4,500 meters per second. So some seismograph in this city here detects the P waves before the S waves, and the time interval between those two detections is 2 minutes. I'll just call that 120 seconds. Let's convert to SI right out the gate here. And we're supposed to figure out how far away this earthquake was. And we assume that the waves travel in straight lines, even though they might be doing something different. They might be following some curved path. And now you're wondering, why would they do that? Well, because as the waves travel, they're moving through different materials. And if the speed through that material changes, then the wave will bend. That's a wave phenomenon called refraction. And we will look at that later in the semester. Anytime a wave enters a medium with a different speed, it's going to bend, which is how your spectacles work if you're somebody who wears glasses or contacts. Okay. Since we're assuming that these speeds are constant, we can go back to one of our kinematic equations. Remember, if something's picking up speed at a steady rate, so constant acceleration, you can use this equation. This is the kinematic equation for displacement at constant acceleration. There is no acceleration. Well, here you could say the acceleration is 0. So we're left with the 8th grade formula, distance equals velocity or speed times time. So let's solve this for the time interval. And this is going to confuse you. I'm using delta t to mean two different things here and here. Right here, this is the time interval between receiving P waves and then receiving or detecting S waves. This is the common usage of delta t in our kinematic equations. So let me now apply this to the time it takes the P wave to go from the epicenter to the seismograph. And we're looking for this unknown distance d, which could be many thousands of kilometers because the Earth is a big chunk of rock. Using this for the P waves, we see that the time it takes for the P waves to arrive, so I'm adapting the notation slightly, T sub P is how long it takes a P wave to go from here to here. That would be the unknown distance d divided by the speed at which the P waves travel, which I will call V sub P. And the time it takes for the secondary waves to arrive is the distance they travel divided by the speed at which they travel. And that, of course, means that the time difference, this being the larger time, right? It takes longer for the S waves to arrive. So let's do TS. Delta T now is TS minus TP. Again, I'm using delta T here in the original sense. That's the interval between the two detections. Different usage of how I used it here. Well, when we subtract this from that, they both have a D in the numerator. So I'll factor that out. I've got 1 over VS minus 1 over VP. And I might as well show you a little algebraic fact that is useful because it shows up so often. You've probably seen this already. We'll probably use this often when we use the thin lens equation later in ray optics. If you want to combine two fractions like this, well, all I'm really doing is doing lowest common denominator, but you end up with the product. Am I doing this right? No, I'm not. Yeah, that's what they call a brain fart. Excuse me. I just want to have these with the common denominator. So that's going to be VP minus VS over VS VP. Yeah, I guess that is what I was thinking of. Difference over product. Is that really any easier calculation-wise? Probably not. Sometimes if these are integers, it's nicer to put it in this form because you can do it in your head. Like if you had a number like 6 and 10, you can take their difference in your head, you can multiply them in your head. Here, maybe not so much because when you take the reciprocal, you'll get a decimal. But as far as calculator calculations, I'll just go with this. So I'm going to take the, oops, man down. Okay. I'm so proud of myself. I've had this calculator for over 10 years now, and I haven't lost it because, I don't know, maybe 15 years ago, I had this really bad habit of losing low value items. Like I'd leave a $10 calculator in the classroom, or I'd leave a coat behind that I was actually really fond of. And I got so irritated with myself for losing these things. I just told myself, I'm never going to lose anything again. And I've been pretty good about that. It's been a long time since I've misplaced anything. That's not wood, but okay. Secondary speed, 4,500. I'll take the reciprocal. I've got a reciprocal button here. Minus, and then the primary wave, 8,000. Take the reciprocal. Hit equals. I do get a positive number. I'll multiply that by, oh, I'm solving for D, right? That's what I want. So let me put that number into memory. And my distance D would be the time interval divided by all of that. Okay. Well, I've already calculated the denominator and put it into memory. So the time interval was the 120 seconds. Divide by that number. And I obviously did something. Did I do something wrong? That's in meters. Let's check the solutions manual. We know the Earth is a big place, but it's not that big. Okay, let me pause. Looks like I'm okay. Let me take the decimal place 3 to the left. I'll write this as 1,000. Oh, fine. 1,234 times 10 to the third meters. Okay, yeah, I just moved the decimal point 3 to the left and paid for that with a multiplication by 10 to the third. And the reason for doing that is we recognize that 1,000 meters is a kilometer. So we can write this as 1,234 kilometers. And that's a number that does make sense because I happen to know, because I've used this number so many times, that the equatorial radius of the Earth is a little squashed. This radius is about 6,370 kilometers. And earthquakes can travel pretty far across the Earth. So this number is reasonable. That's it for this video. I'll present some more solutions in a follow-up video. And I'm sorry to disappoint, but there's no George Michael music at the end of this one.